Alright, let's start with what scheduling actually means. When we talk about scheduling, we are really talking about deciding who does what, where, and when, while keeping an eye on time and resources. In simple terms, scheduling is the process of allocating resources to different tasks over time. So, in a manufacturing setting, that means figuring out which jobs goes to which machine and at what time. The aim here is to minimize delays, cut down costs, and push as much work through the system as possible. That's what we call maximizing throughput. Okay, now think about this for a moment. Every production environment, no matter how big or small, faces the same headache: limited resources and competing demands. You can't have every job done at once, right? That's why scheduling exists. It gives us a systematic way to make these decisions rather than reacting randomly. The goal is to create a feasible sequence of operations that hits key performance metrics like things like make span, tardiness, utilization, and follow time. Make span, by the way, just means the total time it takes to finish all jobs. Tardiness refers to how late jobs are compared to their due dates. Utilization shows how effectively we are using our machines, and follow time is how long a job spends in the system from start to finish. Alright, now looking at this chart here, we have got what's called a basic job shop visualization. You can see different jobs labeled as like J1, J2, and so on here, at missions A, B, and C. The horizontal axis represents time. So for example, mission A starts with job 1 and then moves on to job 2. Meanwhile, mission B starts with job 3 and processes job 4. And this visualization helps us understand how missions and jobs are coordinated over time. The challenge is to find the best order so that machines stay busy without unnecessary idle periods and jobs get done as efficiently as possible. And here uh, we can see our cards. It is NP hard problem, force formulations here, and average example efficiency gain and variance. Okay, let's continue. And now we will talk about how scheduling problems are classified. Yes, not every scheduling problem looks the same. Each has its own rules and constraints, which means the way we approach them changes too. First, we have single mission scheduling. Here, all jobs must be done on just one mission. It is the simplest setup. The main question is, what's the best sequence to minimize total completion time, weighted tardiness, or other objectives? This kind of setup helps us build intuition before tackling more complex environments. Next, we move on to parallel machine scheduling. Now we have got multiple machines working at the same time. They might be identical, similar, or completely different. The trick here is deciding both which machine gets which job and in what order to run them. Load balancing becomes a big issue because we don't want one machine overloaded while others sit idle. And here's a kicker: even simple objectives can turn into NP hard problems, meaning they get computationally tough very fast. Okay. Then there is flow shop scheduling. In this case, every job follows the same route through all missions. Think of it like an assembly line: job 1, job 2, and so on all go to mission A, then B, then C, always in the same order. One common goal in flow shops is to minimize the make span. When we are dealing with two machines, Johnson's algorithm can actually solve that optimally. And here, job shop scheduling. This one's the most general and toughest. Each job can have its own route through different machines. Job 1 might go A to B to C, while job 2 could go to B to A. This setup gives maximum flexibility, but also the most complexity. To represent it, we must, not must, we often use what's called a disjunctive graph, as you can see here, where nodes represent operations and edges represent machine constraints or sequencing. Even small cases can be computationally difficult, but in the real world, this is often the most realistic model for production systems. Okay, and here we can compare schedule types, here single machine, parallel machines like that, and flow shop. Okay, objective function parts and constraints. Yes, when you are building a scheduling model, you need to know what you are optimizing for. I mean, that's your objective function and what rules you can't break, and those are your constraints. Let's go through the common objective functions. What are they? Yes. First, makespan minimization. The goal here is to minimize the time it takes to complete the last job. The notation is C max. Here equals the maximum of C sub j. Here. What is that? Reducing makespan helps increase throughput and lower total production time. Now, total tardiness is here. This one minimizes how much time jobs go past their due dates. The notation is here. Sum of t sub j, where t sub j equals max of 0 c sub j minus d sub j. It is a customer-focused metric because it keeps delivery commitments on track. Then total flow time. Here we minimize how long jobs spend inside the system overall. That helps reduce work in process inventory and improves cash flow. Weighted completion time is another one. It minimizes the summation of that. What is that? Sum of W sub j multiplied by C sub j, where Wj is the weight representing the job's importance. So more important jobs get higher priority. Number of tardy jobs here, which just counts how many jobs miss their due dates. Simple but useful when you care about deadlines or exact lateness. And here machine utilization, maximizing how much time machines are effectively working instead of sitting idle. It's about using resources efficiently. Okay, of course, every scheduling problem comes with constraints. These usually fall into two big categories: temporal and resource constraints. Temporal constraints are time-based. For example, release times mean a job can't start before a certain point. Due dates are the required or desired completion times. Then we have got precedence constraints, that when some operations must finish before others can begin. And setup times represent the transition period between jobs, like cleaning a machine or switching tools. Resource constraints, on the other hand, are about availability and capability. Machines might be limited in number, so jobs can't be interrupted once they start. That's called no preemption. There might also be specific tool requirements or even skill constraints for human operators. Okay, and looking at this bar chart, we can see how different objective functions affect performance. Makespan optimization gives around 85% improvement compared to unscheduled operations. Tardiness improvement is about 72%. Flow time is around 78%. Utilization tops the chart at about 90%. These numbers show that a good schedule can dramatically improve how efficiently a production system runs. Just example, of course. Alright, and let's continue. Moving on, we will talk about how we actually solve these scheduled problems. Because most of them are NP-hard, meaning they grow in complexity faster than computers can easily handle. We need different algorithmic approaches depending on the problem size and the time we have got. Okay, and we will start with exact algorithms. These methods guarantee optimal solutions but can become slow as problems get larger. Branch and bound is one example. It systematically explores the solution space by branching on decision variables while using bounds to prune bad options. It guarantees the best answer but can be very slow for big problems. Then we have dynamic programming. This breaks a big problem into smaller overlapping subproblems, solves them once, and stores the results to avoid recomputation. It's great when the problem has what's called an optimal substructure, but memory usage can become heavy. Mixed integer programming. That formalizes scheduling as a set of linear constraints using integer variables. Modern solvers are getting better and can handle medium-sized problems well. It's flexible, works naturally with complex constraints, and commercial solvers can even provide bounds on solution quality. Constraint programming. This is a declarative way of solving problems by specifying what must hold true rather than how to do it. Is particularly strong for highly constrained problems and works nicely when combined with other methods. Okay, now, since exact methods can be too slow for large-scale scheduling, meta-heuristic approaches come into play. These are more general strategies that guide the search for good solutions without guaranteeing the absolute best one. Genetic algorithms are population-based. They use ideas from evaluation, like selection, crossover, and mutation, to gradually improve solutions. It's like evolving better schedules over generations. Simulated annealing, on the other hand, allows even worse solutions at first, but gradually becomes more selective, much like cooling metal to find a stable structure. It's a probabilistic method that helps escape local optima. Then there is taboo search. This one uses memory. It keeps track of recently visited solutions so it doesn't get stuck going in circles. It's great for exploring new regions in the solution space. Ant colony optimization takes inspiration from how ants find food paths. Virtual ants lay down trails called pheromones to mark good paths. Over time, the best routes strengthen guiding feature search. Variable neighborhood search works by changing the neighborhood structures, basically the way we modify current solutions to escape local traps. And particle swarm optimization. This method is inspired by group behavior like birds flocking or fish schooling. Each solution, called a particle, moves through the space based on its own experience and the swarm's best known positions. Okay, let's cover dispatching rules. These are simple local rules used to make quick scheduling decisions without complex optimization. They are fast to apply but might not always give the best overall result. We have classic priority rules like SPT, which stands for shortest processing time first, get the shortest jobs done early. EDD means earliest due date first, focusing on deadlines. FIFO and LIFO stand for first in, first out, and last in, first out respectively. LPT, longest processing time first, which can sometimes help balance the workload. CR means critical ratio scheduling, that one compares time remaining to work remaining to decide priority. Then we have got composite rows that mix multiple factors. WSPT stands for weighted shortest processing time. ATC is apparent tardiness cost. Covered stands for cost over time. Mode, modified due date. There are also select-based rules that use look-ahead and hybrid rules that combine multiple criteria. Okay. Yes. So now we are stepping into how artificial intelligence and machine learning reshaping scheduling. Traditional scheduling methods, things like heuristic rules or optimization algorithms, work well when our environment is predictable. But as you know, real-world systems rarely behave perfectly. Machines break down, job priorities shift, materials arrive late, and human operators vary in performance. That's where AI-based approaches come in. They bring flexibility, adaptability, and the ability to learn from experience. And AI methods can sense what's happening on the shop floor, make decisions based on what they have seen before, and adjust to new conditions without human intervention. Essentially, the goal here is to build systems that improve over time, systems that can handle uncertainty instead of just following a fixed set of rules. Okay, let's look at the first AI technique, Deep Reinforcement Learning, or DRL. This approach is all about learning through interaction. Instead of being told what to do, a reinforcement learning agent experiments. It takes an action, sees the result, and adjusts based on the feedback. Over time, it figures out which decisions lead to the highest rewards. In scheduling, that means the agent observes the current state of the shop floor, I mean, which jobs are waiting, which machines are free, what deadlines are coming up, and then decides which job to schedule next. The goal is to maximize cumulative reward, like minimizing total production time or avoiding lateness. And deep neural networks sit at the core of this. They approximate what we call value functions or policies. Essentially, they estimate how good a certain decision will be in a given situation, even when there are millions of possible states. And this makes DRA powerful in large, complex environments. Okay, it naturally handles dynamic systems, meaning if the environment changes suddenly, it adapts. It learns directly from experience, so it doesn't need explicit programming for every possible case. It can even generalize to unseen problems if it is trained well. It can handle new situations without starting from scratch. And of course, there is a trade-off. It needs a lot of training, data, and computation. And that's why methods like DQN, I mean Deep Q Network, Asynchronous Advantage Active Critique, or A3C, and PPO, and that's Proximal Pulse Optimization, are commonly used. These are all reinforcement learning algorithms that balance exploration and exploitation in different ways to find good scheduling policies efficiently. Next up, we have graph neural networks, or GNNs. Many scheduling problems naturally form graph structures. Think of disjunctive graphs where nodes represent operations and edges represent constraints like machine order or job precedence. In such cases, GNNs are ideal because they can directly use this structure. So a GNN learns how information flows across nodes and edges. So if one machine operation affects another, the network learns that relationship. This helps it capture dependencies that traditional neural networks would miss. And GNNs exploit the structure of the problem, explicitly meaning they don't have to learn it from scratch. They also scale much better than fully connected networks since they process relationships locally rather than connecting every input to every output. What's more, GNNs can embed entire scheduling graphs into smaller, dense representations called latent spaces. And that makes them useful for learning heuristics, basically shortcuts to good decisions, and estimating value functions that guide scheduling. Okay, let's move to supervised learning methods, which are about learning from examples. What's happening here? Instead of exploring on their own like reinforcement learning agents, models are trained on labeled data, examples of good scheduling decisions, and they learn to imitate those. And there are two key approaches shown here, learning prior to rules and learning to branch. In learning prior to rules, we train a model to decide which job should go next based on the current state, things like remaining processing time, due date, and machine load. It's similar to traditional dispatching rules such as shortest processing time or earliest due date. But now the model learns these rules automatically from data. Over time, it can produce more sophisticated decisions that get close to optimal results. And this approach works fast during deployment because inference, that's the process of making predictions, is quick. It also allows the model to combine multiple features intelligently rather than relying on a single factor. However, it does require labeled data for training, which means someone must provide examples of optimal or near optimal schedules first. The most common algorithms used here are random forests and neural networks. Then we've got learning to branch. What's that? This one connects to exact optimization methods like branch and bound algorithms, which are used in solving mixed integer programming problems. Normally, these algorithms explore a massive decision tree, deciding where to branch at each step, and that can be computationally expensive. Machine learning models can be trained to predict the best branching decisions. They imitate expert strategies, so instead of exploring blindly, they focus on promising paths, dramatically speeding up computation while maintaining optimality guarantees. This approach uses imitation learning where models learn from expert solutions. It's an active area of research showing strong results for large-scale scheduling and optimization problems. And here, hybrid AI approaches mix the best of both worlds, machine learning and classical optimization. Each has its strengths. Optimization provides mathematical rigor and guarantees, while machine learning provides flexibility and adaptability. Combining them allows us to build systems that learn and improve while still staying grounded in proven theory. Okay, for example, in ML enhanced native heuristics, machine learning adjusts parameters to choose operators dynamically during search. Instead of using fixed settings, the algorithm learns what works best for a given problem instance. Then we have neural combinatorial optimization. These are neural networks that produce solutions directly. For example, generating sequences of job orders. They use mechanisms like attention, which helps the model focus on important parts of the problem, and pointer networks, which handle variable length outputs. This approach is great for end-to-end learning, meaning the network can take raw problem data and output a schedule without traditional optimization steps. Predictive scheduling, on the other hand, looks ahead. It uses time series models or neural networks to forecast disruptions, say mission failures, changes in demand, or material delays. By predicting these events, the system can proactively adjust the schedule before problems occur, which makes it valuable for dynamic real-time environments. Here we have got the performance comparison chart. The horizontal axis shows execution speed, while the vertical axis shows solution quality. You can see that traditional heuristics sit lower on the quality scale even though they run quickly. And as we move forward, graph neural networks and reinforcement learning methods produce higher quality solutions, although they take slightly more computation time. At the top right, here, hybrid AI methods stand out. They balance both speed and solution quality effectively, offering the best trade-off between accuracy and practicality. Yes, that page is done. Let's continue. Now, there is nothing actually, just interactive parts. Here, you can see Gantt chart visualization, and let's change our parameters. Number of jobs now 6 and 7, 8, 9, 10. Everything is changing. And number of missions now 3, and watch me 4 and 5. And processing time reliability, here you can see the change. Number of jobs, and everything is increased. Okay, and here some cards. Make span, utilization, average flow time, total idle time. That's just toy. Okay. Now, let's look at how all this plays out in real industries. AI-based scheduling is not just theoretical, it's already being used in sectors like semiconductor manufacturing, pharmaceuticals, aerospace, steel, food processing, and healthcare. Each of these industries faces unique challenges, but scheduling remains at the core of efficient operations. Look at this. In semiconductors, we see efficiency gains of about 45%, which is a huge given the complexity. Second, follow with around 35, third about 40%, still around 30%, food processing near 32%, and healthcare at 38%. You can see a pattern here. The more complex the environment, the higher the potential payoff from the intelligent scheduling. Across industries, the main benefits are clear: shorter production cycles, less work in process inventory, better use of resources, and improved on-time delivery. In other words, smarter scheduling leads to faster, more predictable operations at lower costs. Okay, let's break this down a bit further. Here, there are hundreds of operations per buffer, and the same buffer may revisit missions multiple times. That's called a re-entrant flow. Batch processing, setup constraints, and cycle time minimization are key concerns. Since the equipment is extremely expensive, keeping it utilized is a top priority. And secondly, here, batch processing dominates too, but here we have got strict validation requirements, sequence-dependent cleaning times, and even expiration dates or materials. Regulatory compliance is a major factor, and planning campaigns helps manage those restrictions efficiently. Aerospace assembly is all about complex precedence relationships. You can't install a part before its support structure is ready. Add to that long lead times, limited skilled labor, and high tool costs, and you get a scheduling challenge that's both time critical and resource intensive. Steel manufacturing combines continuous and batch processes. The setup costs are high, so plants often schedule long campaign runs. There are also temperature and energy constraints along with blast furnace scheduling, one of the toughest problems in process industries. And food processing adds a different layer. Here we have got perishability constraints, shelf life limits, sanitation requirements between products, and seasonal demand changes. Even allergen management affects sequencing decisions. So schedules must balance safety, freshness, and efficiency all at once. And finally, operating room scheduling, and non-manufacturing but equally critical example. Hospitals have to manage surgeons, equipment, patient priorities, and emergency cases, and procedure durations are uncertain, and multiple resources need to align perfectly. Here, AI can make a huge difference by coordinating all these variables in real time. And across all these examples, the gains are tangible. Efficiency improvements of 30 to 50%, lead time reductions of 15 to 25%, work in progress inventory cuts of 20 to 35%, and annual savings between $2 and $5 million for medium-sized plants. That's the real impact of smart scheduling driven by AI. Not just theoretical optimization, but measurable business outcomes. And thank you for listening.